Stefan for the final presentation. Stefan, the floor is yours.
Yes, thank you. So I'm going to talk about measuring and mapping light pollution, which was my project last year. And to start off, I would like to explain what is light pollution. So light pollution is a very broad concept. Everyone can understand something different. So an astronomer or a biologist understands something different than a car driver. So this chart here shows what different kind of light pollutions can occur. And what I was concentrating on was this light pollution that ended up in the sky. And the definition is therefore the part of light that ends up in the sky and is consequently not for functional use. So what is functional use? This is the simple illustration for a pristine night sky, and we can see if we put some lamps, then the light ends up in the sky. And if we shield it, so we can limit the light pollution. So this is the whole concept of controlling light pollution. There are a lot of detriment effects on health for people and animals. So there are nocturnal insects that die because they are attracted by the light, and consequently there are ecological consequences. There's an effect on bird migration, and of course astronomers, they cannot see the stars anymore, so they are bothered by this light. And generally we talk about this term loss of the night. There are maps that are available. This map A is rather known, so it has been circulated over the internet and used very often. If we zoom into this map, this is Switzerland, so we can see there are some detail, but if we zoom even further in, then we can see that the resolution is not very high. So we can see a pixel of about 700 meters. So that's the best we can get from a satellite at the moment. There are modeled maps like this from a scientific in Italy. And he has provided this map to the Dark Sky Association, who cares about the night sky. We can see not much more details. On my town is here in Winterthur, and if I zoom in, so I see the whole town as very light polluted. I flew over Switzerland recently, or during the time I was working on the studies. So I took this picture in B. This is over the Lake of Zurich, and I imagined it should be possible to get a map of an area in that quality, seeing streets, seeing details, and with a good resolution. So that led me to my research question, which I wanted to apply to the research area around my hometown in Winterthur, in the northern part of Switzerland, a city of 100,000 people with populated areas, with agricultural areas here, with woods. So it is quite a varied area. So the research question was, what is a suitable setup of a GIS-based model to produce an upward light emission map? And what is the significance that the map can achieve? So I don't go into the details, but in the end it was important, of course, to see whether this map I wanted to produce is accurate. Research method, I had basically two fields of activity, desk and field research, and then the part of modeling and visualization in ArcGIS. in the desk and field research, I went out to see what light sources are there. I had to understand what is the propagation of light. I did some measurements, then I did some modeling with the measurements I took. I visualized it and I came up with a map which I validated against the reference image, which I still had to find. So this was the observation part, going out and seeing what lights are there. So motorways, they have completely different light sources than a residential street light. Sports fields, they have very different light sources. So I came up with, I clustered these different light sources into 10 categories, mainly street light in the first 4, then lights from residential building, from industrial buildings, lights from train station, from sports pitches, so the football field, for example, from parkings, and light from Old Town, where there are a lot of shops and light sources concentrated at a small area. So for the measurement part, I went out with this so-called light meter, lux meter, and I measured each of these categories in the field. So this is from the side, this is from the top. So I had to find out how this light propagates from the source, which is M1. So of course here the light is fainter than somewhere in the middle. And I was with a mobile device to capture this data, and which I then put into a database and processed it, and finally applied the formula of the light propagation to each light point, which is shown here. So this is a street, light points, the formula, and then I modeled it in ArcGIS, how this light propagates. So intense in the middle, then it fades out towards the edges. So this was done for all the categories, for all the light points. So residential buildings had the most light points. So almost 100,000 light points were modeled like this. In ArcGIS, it's so putting all the layers together, it gets out in black and white. So I had to find a way to visualize it in a way that looks natural. So I took aerial images from another project, from a light pollution project in Geneva, and applied the RGB values, because I knew that they use the same light sources in that city. And that was finally the light pollution map of the research area. And if we compare with what the satellite has provided, so we can understand there's much more detail. So a very detailed view into the street looks like this. The individual lights here, a day view where I put the lights with these yellow circles. So we can understand how this particular area looks during nighttime. So finally, I wanted to understand whether my calculations are also valid. I was looking for a good reference image, which was really difficult to find. The only one I could find was a one by an astronaut, Paolo Nespoli from ESA. He took this image over the Lake of Zurich here, and my research area in this very little patch here, unfortunately. So an image taken by a DSLR camera, so a normal Nikon camera, and I processed it in a way that I compare it with my modeled image, and I compared these two images. I used a green band for this and came up with a with a calculation of how accurate my image is compared to the photo from space. So this is the result. So I understood that the modeled result is quite accurate, of more than 75% of pixels that are with no significant difference. There are some deviations from the two images, which I map here. So the blue ones are points which look more intense in the NASA image than in my modeled image. So I, of course, wanted to find out what are these spots here. So there are many of those which are really blue, so a large deviation. And I found out that there are some issues. For example, this point A. If we go into it more deeply, so this is the NASA image here. It's very, very bright. If I analyze it on my modeled image, I can see there is a large outdoor sports area, which was at the time when the NASA astronaut took the image, was very enlightened. And in my model, I excluded this sports area because I assumed they are not on for 24 hours. So that is one of many reasons why there are some deviations between the two images. So applications was one of the aims to find out, well, how can this be used? So such a local map. So I found out three main areas. Awareness. So with such maps, one could raise awareness of the light pollution issue, inform citizens. Another use could be by astronomers, so they could have an interest in finding the good spots to look at the sky, so to look at the stars. So such an image could give information, such a map could give information regarding this. And a third application could be optimizing light emissions, of course. So with scenarios, we could modify the model and see what is the outcome if we just if we lower the light by 10%, or if we have different time patterns in lighting the streets. So there are many ideas that could be interesting. So the conclusion is that satellite imagery is currently not sufficient for the visualization at a local scale, and that a modeled approach, as I worked out, could be promising to come up with maps that are more detailed. So summarized, GIS modeling and visualization can help to enhance the understanding and control of light pollution. So many people have supported me, so thank you. Thanks to all of them. Otherwise, it wouldn't have been possible.
Thank you, Stefan.